So simply an AC drive, once again, it's simply the configuration that consists of a power electronic device and a controller that will be responsible for the control of AC motors. You have the power electronic devices, and you will have different types of controllers that will be responsible for the control of AC motors. Now we are talking about speed control, position control, torque control, current control of AC motors. Now the power electronic devices that will be used in case of AC motor drives. For a DC drives, we had rectifiers and choppers. For power electronic, in case of AC drives, the power electronic devices that will be used, they can be inverters or they can be cycloconverters. So the output of inverters and cycloconverters is an AC output. So using these power electronic devices, we'll be able to control the speed of the AC motor. While as the controllers, they can again be the same controllers, PPI or artificial intelligence based controllers. And as far as the AC motors are concerned, that different types of AC motors that are used in the industries, they consist of the induction motors mainly. Primarily, most of the industrial loads is dependent upon induction motors. You have the permanent magnet synchronous motors, or you can simply say the synchronous motors. They are fairly used as well. You have reluctance motors. You have BLDCs. Fine. So the configuration that consists of a power electronic device and a controller responsible for speed, position, current control of the AC motor is known as an AC drive. Here the power electronic devices will be inverters or cycloconverters, whereas the AC motors can be induction motors, PMSMs, reluctance motors, or BLDC motors. They are the most commonly used ones. We have others as well that can be used, and you can accordingly control the speed position of those types of AC motors as well. Now, talking about uh, traditionally, the AC drives were primarily used as fixed speed drives. So wherever there was a fixed speed operation, like in case of water pumping or uh, like in case of water pumping, we had a we required some fixed speed. We do not want the control of speed. So traditionally, AC drives were employed in such applications, and DC drives were actually used uh, in variable speed applications. So this is what was the traditional approach. AC drives were used for fixed speed applications, while as DC drives were used for variable speed applications. The reason for this being that DC drives were simpler and there was an inherent decoupling. So the control was easier in case of DC drives as compared to the AC drives. While as in case of AC drives, the speed control was much more complex and there was a coupling, a natural coupling between flux and torque. So because of those reasons, AC drives were preferably used for fixed speed applications only and not for variable speed applications. But over the last few decades, with the advancement in semiconductor technology, with the advancement in control schemes, what we have seen is there has been a shift from DC drives to AC drives. So in the last few decades, there has been a shift from DC drive systems, the use of DC drive systems, to AC drive systems. Now this shift has taken place because of advanced semiconductor technology. So this shift from DC drives to AC drives has taken place because of advanced semiconductor technology, advanced controllers, as well as because of the modern control approach. So initially, whatever controls approach we were using in AC drive systems have now been shifted with modern control schemes. Uh, Fine. So nowadays, AC drives are now used in wide speed range applications as well. We are not now limited. Uh, we do not have DC drives limited to variable speed applications. We are now using AC drives predominantly in variable speed applications. That was not the case earlier. Because in 1960s, 70s, we can say that DC drives were more dominant and they were preferred in variable speed applications because there's speed control was simpler, whereas there was an inherent decoupling between flux and torque. So AC drives did not find much use as compared to DC drives. But over the last few decades, AC drives have there has been a shift from DC drives to AC drives, and this shift has taken place because of advanced semiconductor technology, advanced controllers, modern control approach, and inherent advantage of AC machines. As far as the AC machines go, they are much more uh, economical. They are rugged, reliable as compared to DC motor drives. They have better speed and torque response, uh, speed and torque profile rather. Because of these inherent advantages of AC machines, uh, we have now shifted to these AC drives. Now, the most important AC motor that actually covers almost 80%, 90% of the industrial applications are induction motors because of its uh, because of the uh, use of induction motors in so many applications in industries. It's actually referred to as the horsepower of industries. So the first motor, the AC motor that we'll be studying, the control strategies that we'll be studying will be associated with the induction motors. So we'll be taking up the induction motors first, then we'll be taking the synchronous motors. So induction motors, they find a lot of use in industries, and that's why they are known as the horsepower of industries. Uh, they are they have a pretty rugged construction. Uh, they have much more economical. Rugged design and economical. They are economical as well as reliable. These features actually make it uh, well suitable for a number of industrial applications. Uh, so, induction motors have been used over the last few decades. Uh, Again, I'm repeating, in the industries, They are being used uh, in a number of applications in a number of industrial applications. So we are starting with the induction motors. So as far as the speed control strategies of induction motors go, there are three important types of speed controls that we are employing nowadays in induction motors. One method is the scalar control method. Second method is the vector control method, and the third one is the direct torque control method. So they consist of a number of subtypes as well. So scalar control method, simply stating, as the name indicates, it's scalar control. That means here we are only dealing with the magnitude control. You know what scalars mean? So scalar in scalar control of induction motors, we are only dealing with the magnitude control. That means we are changing the magnitude of voltage, magnitude of frequency, and accordingly changing the speed of induction motor. While as in case of vector control strategies, as the name vector indicates, we are dealing with magnitude as well as phase control. So we are not only changing the magnitude of voltage and frequency, but we are also changing the phase um, between the voltage. Uh, so uh, because of this vector control strategy, there are a number of advantages associated with a vector control strategy that we'll study gradually. These are two types of speed control strategies. Now there is a third type that has been introduced in the last decade or so. That is the direct torque control strategy. In case of direct torque control, what we are doing is we are directly controlling the torque of the induction motor. So we have three strategies. One is the scalar control method. In scalar control method, we are only dealing with the magnitude variation of voltage and frequencies, and accordingly we are able to control the speed position of the induction motor. In a vector control strategy, we are dealing with magnitude and phase of the induction motor. Fine, and accordingly we'll be able to control the speed, torque, flux of the induction motor. In a direct torque control strategy is sometimes referred to as an advanced scalar control strategy, or sometimes it is referred to as a vector control strategy. So instead of grouping it under scalar control or vector control, we can say it's a separate control strategy. And in case of direct torque control, we can directly uh, we are directly dealing with the control of torque. We are not here controlling the speed and eventually controlling the torque. In case of direct torque control, we directly control the torque of induction motor without actually controlling the speed of induction motor. So, direct torque control strategy, it actually combines the advantage of both scalar control and vector control somehow. Uh, so it has found a lot of use in the last decade. So these are three control strategies. So to understand this, to understand the scalar control and vector control or the director control, we have to first of all understand the mathematical model of induction motor. There are two mathematical models that we'll be studying. One is the steady state model of induction motor, and second one is the dynamic model of induction motor. So as far as the steady state model of induction motor goes, this will be amplified by scalar control strategies. Since a steady state model will only give us the steady state values of current, voltage, losses, power losses, etc. Whereas a dynamic model will give us a better picture of the dynamic and the transient behavior of the currents, voltage uh, in different quadrature components. So as far as the steady state model of the induction motor goes, that we have actually already studied, it's nothing but the equivalent circuit of induction motor. This is a per phase equivalent circuit of an induction motor. The equivalent circuit of induction motor, you have already designed in your machines course how uh, the equivalent circuit is basically constructing using the known losses in the induction motor, whereas you have the stator copper losses, you have the rotor copper losses, you have the leakage flux associated with the stator windings, you have the leakage flux associated with the rotor windings, and then you have the core loss components RC and XM. So using that knowledge of power losses in the circuitry, you can derive the equivalent circuit of an induction motor. So as far as the equivalent circuit of induction motor goes, this will give you actually the steady state components of the induction motor. That is, it will help us calculate uh, IAS, that's the current in phase A of the stator. Accordingly, you can calculate the current IR. You can calculate the rotor copper losses I square R. You can calculate the stator copper losses I square S RS. You can calculate the leakage flux associated with the stator reactance XS. You can calculate the rotor leakage flux associated with XR component. You can accordingly calculate the core loss by finding out the resistances RC and XM and the current flowing through these branches. So once we have calculated the losses, we'll be able to derive the efficiency. So all in all, the steady state model only gives us the steady state profile or the steady state behavior of the induction motor. The losses, the efficiency, currents, steady state values of currents, steady state values of the voltage. You can calculate slip of the induction motor using the equivalent circuit or by knowing the speed of induction motor. So all these values, the steady state values, as well as the speed, torque, etc. But the steady state values we'll be able to calculate using the equivalent circuit of induction motor. So this is referred to as also the steady state model of the induction motor. So this model, this equivalent circuit can be useful uh, for finding out for scalar control strategies. So the steady state model is useful for scalar control of induction motor. The second type of mathematical model that we'll be doing in the next session is the dynamic model of induction motor. So that dynamic model will help us uh, obtain the vector control, will help us in understanding the vector control of induction motor. Now there are some basic uh, fundamentals, basic concepts about induction motor that again you have actually already studied in your machines course. Uh, so one is the production of rotating magnetic field. So you already know how a rotating magnetic field is produced by three-phase currents in case of any AC machine, in case of any polyphase AC machine. How a rotating magnetic field is produced. Fine. Uh, Secondly, you have the torque production. Now, you know, in case of an AC machine, uh, say for example, we have the induction motor, we are supplying the stator windings with this, we are feeding the stator windings with a three-phase AC voltage. Uh, what happens is that current flows in the stator windings. This current results in production of a stator rotating magnetic field. The stator rotating magnetic field induces voltage in the rotor windings. Since the rotor windings are shorted, uh, a rotor current is established. That rotor current leads to production of a rotating rotor magnetic field. So you have a stator magnetic field and you have a rotor magnetic field. Both are rotating at the same speed, that is the synchronous speed. Because of the interaction of the stator magnetic field and the rotor magnetic field, torque is produced as per the equation. Tau is equal to Bs cross Br. So this is actually a cross product of the two magnetic fields, the stator magnetic field and the rotor magnetic field. Hopefully, you will go through these concepts at your own. Uh, Go through how the rotating magnetic field is produced. Go through how a torque is produced in case of any AC machine. So, just to summarize what we have studied so far today, we have We have an AC drive now. We are already done with the DC drives. In case of AC drives, again, we are now controlling the speed portion of any AC motor, be it an induction motor, a PMSM, a reluctance motor, or a BLDC motor. And the power electronic devices that will be now used in case of AC drives will be inverters and cycloconverters. As far as the AC drives go, they are much more complex than a DC drive. Uh, the mathematical model that we'll be actually studying in the next class, a dynamic model of induction motor. It's much more complex and new to you that you have not actually studied previously. Now, besides this, we discussed how we shifted from DC drives to AC drives. What were the reasons that led to the shift from DC drives to AC drives? So now, as far as the induction motors go, we have started with the induction motors. We have three types of speed control strategies in case of induction motors. They are the scalar control method, the vector control method, and the direct torque control method. The scalar control methods, these methods we have actually already studied. Scalar control method simply states that you are changing the magnitude of voltage or frequency to control the speed of induction motor. So some of these methods you have already studied, like simply by changing the armature voltage, you can change the speed of the induction motor. By changing the resistance of the rotor windings, you can change the magnitude of current in the rotor windings. You can accordingly change the speed of induction motor. By changing the number of poles of an induction motor, you can change the speed of induction motor. So these methods, voltage control, frequency control, by changing the number of poles, by changing the rotor current, some of these methods you have already studied in your machines courses. We'll be taking, we'll be just going through them. We'll not be doing them in detail. So here we are only talking about the magnitude control of voltage, frequency, current, or even resistance or poles for that matter. We are only dealing with the magnitude control. And by magnitude control, how we are able to control the speed of induction motor. Speed control strategies, the scalar control, the direct torque control, and the vector control. In scalar control, we'll be simply dealing with the magnitude control of voltage, frequency, current, or poles. Fine. And accordingly, speed variation, control of speed can be achieved. In vector control, we'll be dealing with both magnitude as well as phase control, and accordingly, speed and position control, torque control will be achieved. What will be the advantage of vector control or scalar control strategy, that will be discussed later on. And the third type of control scheme that is finding increased use in the recently is the direct torque control strategy. In case of direct torque control strategy, we take the advantage of both scalar control as well as vector control, and we are actually simply directly controlling the torque of induction motor. We are not controlling the torque via speed control here. So these are the three control strategies. To understand the three control strategies, we need to understand the mathematical model first. You have the steady state model and you have the dynamic model. We have not taken up the dynamic model yet. The steady state model is simply the equivalent circuit of induction motor that you have already studied in your machines course. This equivalent circuit is derived from actually the when you actually derive the equivalent circuit, you start with analysis of losses. You study what are the stator copper losses, what are the rotor copper losses, what is the leakage flux associated with the stator windings, the leakage flux associated with the rotor windings, the reactances of the stator and the rotor, and the core loss components. And accordingly, using those information of the losses, you are able to derive the equivalent circuit of the transformer as well as of the induction motor. Fine. We actually derive the equivalent circuit of transformer and induction motor is fairly similar to one another. So this steady state model will only give us the information related to the steady state parameters of the system, be it the losses, the power losses in the system, the efficiency of this system, the voltage, the current, the torque produced by this equivalent circuit, the speed produced by these steady state values of currents, etc. So only the steady state information is provided by this equivalent circuit of induction motor. So this model will be used for uh, steady state analysis and accordingly for scalar control of induction motor. While as for understanding the vector control of induction motor, we will have to derive the dynamic model of induction motor. That we'll be doing in the next session. But before that, you have to go through some basic concepts. You have to revise these concepts. They are fairly, you have already studied them in the machines course. We do not have to, I do not have to revise them for you. You can revise them on your own. That is the production of rotating magnetic field. How a rotating magnetic field is produced in case of any polyphase AC machine. Fine. Because of the sinusoidal nature of the three-phase currents or the polyphase currents, and how a torque is produced using um, how a torque is produced because of the interaction of the two magnetic fields. That will be the stator magnetic field and the rotor magnetic field. So these concepts you can revise them on your own. Go through these concepts once again. Uh, so in the next session, we'll be first starting off with the scalar control of induction motor. Then we'll take up the dynamic model of induction motor. Then deal with the vector control of induction motor. So that's it for this session. I hope you'll revise the concepts regarding the rotating magnetic field and the torque produced in case of AC machines. In case of any questions, post them. I'll be ending the meeting.